All right, hello. So we're looking at the tangent and velocity problems here. This is our first first video on this topic, first set of slides. So let's go ahead and look at it. So what the tangent problem is, so-called tangent problem, the idea is that given a curve, we want to find an equation of the tangent line at a specified point. So what we mean by tangent line, the tangent line to a curve at a point is a line that just touches the curve in such a way that both the line and the curve are going in the same direction. So the idea is, if we've got something like, I don't know, let's say we've got a curve like this. A tangent line would be sort of line that would look like that, just barely touching it at that point there. So at a point, that's what we're talking about here. This would be our tangent line. And it just touches the curve in such a way that both the line and the curve are going in the same direction. It's a little bit hand wavy, but what we mean is if you look locally, they look like they're going in the same direction. In this case, going up from left to right. So that's as opposed to something like this green line here. We wouldn't call that a tangent line. So that wouldn't be a tangent line, but something like red line there, that would be another tangent line, in this case at that point. So that's the sort of thing we're looking at. Now, when we're looking at this problem, we have a point on the line. It's the point that's given to us. And so what we need is a slope to give this equation of the line, right? Two things you need for an equation of a line. We need point and the slope. So we have the point, now we need the slope to figure that out. So to find the slope of the line, we use our usual equation there, our usual formula. So you take, you've got 2 points, x1, y1, and x2, y2. So you've got 2 points on the curve. The idea being we've got some curve like this. This point here, maybe, sorry, what I mean is, if we've got a line that we know exists and we want to try to describe it, we find a point on it and a second point on it. Having those 2 points, we can figure out that slope. But the problem here is that we don't know a second point on the tangent line. We have the one, but we don't have the second one. So that's our issue. We do know a bunch of points on the curve, we just don't know a second point on the tangent line. So we can look at what are called secant lines. Now a secant line to a curve is a line through 2 distinct points on the curve. So what we have in mind is something like this. This would be a secant line. Got this nice curve, this blue curve here, and the gold thing there, it is a line. It goes through 2 points, this point and that point. So that's an example of a secant line, as opposed to a tangent line, which would be touching just at that single point going in that direction. It might touch again somewhere down the line on the graph, but locally just at one point. So that's a secant line. There we've got another secant line to that same point, and now through a different second point. So the information that we're given is we're given an equation for the curve, say y equals f of x for something. And so we could find these different points along the curve, but we couldn't find different points along the tangent line. So how is this useful? Well, this is the whole idea. I don't know why I did it that way, but solve the tangent problem, we're going to find better and better and better and better and better approximations to the tangent line by using appropriate secant lines. So what do we mean by that? Well, the idea is if I've got this curve, let's suppose I've got some curve like this, let's say. And my point that I'm trying to find, let's find the tangent line at this point here, right? Now, it's going to be something along the line in this direction, but I don't have a second point on that tangent line to be able to describe the slope. But if I look at, pick a couple points, let's say out here, maybe out here, out here, and I see that line, that line, that line. These are all secant lines. They don't look to be quite good approximations of the tangent line, but you'll notice that as this point is getting closer and closer to the green point, which was my point where I wanted to find the tangent to the curve at, as that gets closer and closer and closer, kind of moving this way, we get really close, 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 and it starts to be that this secant line that you create is not going to look hardly any different than what the actual tangent line would be. So that's how it's useful. We get closer and closer and closer. Again, to solve the tangent problem, we find better and better and better approximations by using appropriate secant lines. And by appropriate, what it is you're shrinking that length from the point in question out to your second point. Get closer, closer, closer. We want this to shrink down. As we get closer and closer, we get a better and better approximation. That approximation is approximating the tangent line. Okay, so we've got an example here. I'm just computing slopes of secant lines just to get kind of used to some of the computations you might end up doing on these types of problems. So we want to find the slope of the secant line. Remember, what we're going to use here is y2 minus y1 over x2 minus x1. In all cases, this is going to be one of our points, and then we'd have 4 situations here for the second point. So if I look at this first one, f of 2 is going to be 8 minus 4, it's 4. F of 1.2 is, let's see, 8.4, sorry, 4.8, get things a little switched there, minus, I guess, 1.44, should be 3.36. F of 0 is 0, that's easy. And f of 0.9 is 3.6 minus 0.81, which I guess is 2.79. Okay, so for number 1, the slope would be, let's take 4 minus 3 over, those are my y values, 4 minus 3 over 2 minus 1, and that gives me 1 over 1. So my slope of the secant line through those 2 points is 1. For the second case, and it's going to be 3.36 minus 3 over 1.2 minus 1. Again, y values divided by x values, the differences. And that's 0.36 over 0.2, which is 1.8. Third example. One thing you can notice here is that, these xy pairs match up. But of course, you can flip the order and nothing will change. So instead of using the new point information, I could use the given one. So 3 minus 0 over 1, that's the corresponding x value, minus 0, that's 3. And the slope in the third case, I could say 3 minus 2.79 over 1 minus 0.9, which is, I think, 0.21 over 0.1, which is 2.1. So those are all our answers there. And so really all it is just using this formula and doing your slope computations that you've done many times in like a pre-calculus class or other classes. Alright, so let's see what we got. So just to clear things up, it looks like we want to know what's happening at at 1, so we could say, well, at 0.91, that's the one in question, 1.2, 2, these are some of the computations that we made. And we found that our m was, well, at 0 it was 3, at 0.9 it was 2.1. Here, that's what we don't know. Here it was 1.8, and here it was 1. And so, just getting closer to 1, it looks like it's decreasing. And going from 2 back to 1, it looks like it's increasing. It looks like, just trying to guess what it is, a reasonable guess here might be 2. Now, we're not going to play the guessing game moving forward. We're going to know how to compute this, but the idea is if we wanted to find the tangent line at the point 1, 3, we might guess that that slope is pretty close to 2. Here is y equals 4x minus x squared, the graph of that. So our point in question is at 1, 3. The first computation we made was looking at the slope from there up to this point, that secant line, and that has slope equal to 1. Then we said, what about 1.2? That had slope 1.8. The next one we computed was at 0. That had slope 3. It was a steeper one. And then we did at 0.9. That one you can hardly tell the difference from what the tangent line would be. And that one has m for slope 2.1. So again, the idea being, let me do this in different colors here. At that point there, we've got that point there, we've got this point here, we've got this point down here. Our point in question is the red point there. As we get closer and closer, that secant line is becoming a better and better approximation of the tangent line. So the actual tangent line, something pretty close to that. Now it turns out the tangent line slope is 2. And we'll see how to do that using some methods further down the road. That's the first big idea of calculus. So this is just an introduction. We're talking about the tangent problem and the velocity problem, and this was our discussion of the tangent problem.